Hello, I am Andrew Stevens' avatar. The real Andy is a Doctor of Technology candidate at Purdue University and a year 2000 graduate of Perry Meridian High School. He has been helping coach a VEX IQ robotics team at Jeremiah Gray Elementary School in Perry Township, Indianapolis, Indiana. One of the required elements of VEX IQ competitions is an autonomous skills challenge, and I wanted to help teach our VEX IQ programmers how to approach this challenge. This video, the second in a series, is generally for 4th to 6th grade students and will rely on using VEX Code Blocks. This video is an intermediate video, meaning that I expect viewers to already have some background in programming on VEX IQ's Blocks platform and to have watched the first video in the series. In our first video, we programmed the robot using relative orientation. This means that every turn or movement was based on the robot's current direction, like saying, turn 90 degrees to the right from where you're facing. However, as we discussed, when the firing command is given, the robot can jump or shift slightly, causing it to misalign. I have updated our code from the first video to simulate this random jump into the program. After each fire command, the robot will move a random amount of 2 degrees in either direction from its current direction. If these small errors aren't corrected, the robot's aim will get worse and worse as the event continues, making it difficult to hit the target. I will leave this code in for the duration of this video to show you how to fix this error. To solve this, we need to use absolute orientation. This means the robot uses a fixed starting point where 0 degrees is always straight ahead based on the starting position of the robot. Turns are based on moving the robot to match specific points on a compass-like system. This helps the robot always know where it is and return to the correct direction, even if it shifts or jumps. The robot navigates using headings, which are angles measured in degrees. Think of it as following a compass, but instead of north, east, south, and west, it uses numbers like 0, 90, 180, and 270. For example, 0 degrees is straight ahead from the initial starting point of the robot, 90 degrees is to the right, 180 degrees is turning completely around, and 270 degrees is to the left. Programming with headings lets us control the robot's direction precisely so it stays on track. Remember, this is based on what you declared the front of the robot to be in the settings. I will use this simple compass throughout this video to help keep you orientated to the headings. To make this system even better, we pair absolute orientation with a gyroscope sensor. A gyroscope is like the robot's sense of balance. It measures how much the robot has turned and in which direction, even if it gets bumped or shifts. In Gen 1 brains, it is a separate sensor that must be attached to the robot. With Gen 2 brains, it is included in the device. Using the gyroscope, the robot can constantly check its direction and fix itself if it starts to go off course. This combination of absolute orientation and a gyroscope keeps the robot accurate and generally reliable, no matter what happens during the event. Let's watch this in action. You will notice that the front of the robot is the part with the orange grabber on it. I have also added the compass to the screen in 2 places. As the robot goes through the actions, notice the monitor on the right side of the screen. You see the reading from the gyroscope providing the drive heading in degrees. For this example, I have suppressed the vibration simulator until after the second pitch, so you can literally get your bearings. The first error was only 1 degree to the right. The second error was 1 degree to the left, which actually fixed the first error. The third error was 2 degrees to the left, followed by a no-error pitch. This is enough to cause an eventual miss. This next part I have said it before, but I need to say it again. I want to remind you that VEX programming should be carried out by the youth teams. As such, I am only providing cursory instructions on how to approach programming autonomous activities. It will remain up to the teams to fine-tune and add additional controls to optimize the program. I will work to create some additional how-to programming guides teaching additional areas of programming that can be explored. But I will attempt not to show a complete program that would work in a real-life environment. As many adults may be watching this, you are able to help within the rules. The teams must always be present for hands-on work. In this case, this means that teams should be the ones writing the final code. In my opinion, this does not mean you cannot help. In fact, I have had to do some coding in this tutorial to be sure I understood what I was teaching the teams watching. I have been an amateur coder since the late 1980s, and I cannot remember ever having a complex piece of code work on first pass. I encourage parents and coaches to co-code, but allow the team members to be the final arbiters of what goes into the robot. For the following steps, we will assume that you have set up your device's brain appropriately. In my work with my son's robot, I found two issues that held our programming up for several hours. First, be sure to enable your gyro. For Gen 2 brains, be sure to select the brain internal from the setup menu. Second, ensure your wheel size and gear ratio are set up correctly, and you pick what direction is forward on your robot. In early work with our BenchBot, I found that if you send the robot out backward first, the device becomes unable to correctly measure turns, and it gets stuck in an infinite spin. Long story short, set forward as the direction you want the machine to move when starting. Remember, this doesn't have to be the same as when you are under manual control. Let's jump into the code. Let's begin by duplicating the entire Action Manager block from our first video. Right-clicking on the When Started event and select Duplicate. Next, let's disable the original block by right-clicking and selecting Disable Block. This allows us to reference the first block without it running in the active program. We can take this time to update the comment on the old block to state that it uses relative orientation and the comment on the copied block that it uses absolute orientation. For our code, add the drivetrain command, turn to the heading before each and every move forward or backward command. The combination of a heading followed by a distance is called a vector. A vector not only tells the robot where to go and how far, but it also helps ensure that the robot stays accurate, even if small errors happen during movement. By using a heading before each distance command, the robot checks its direction and makes corrections before moving forward or backward. For example, if the robot shifts slightly off course during a previous move, the next vector will realign it to the correct heading before it travels the next distance. This constant realignment ensures that even small mistakes like bumps or uneven turns don't add up over time. By following a vector for every move, the robot can stay on track and reach its destination more precisely, no matter how challenging the field or task may be. Our next step is to disable all of the turn right or left blocks in our new Absolute Orientation Action Manager and begin adding the correct directions to each of the headings we added in the prior step. Our first heading is to move straight forward. We will set this block to a heading of 0. Our second heading is a turn to 90 degrees prior to moving in reverse for 400 millimeters. Our third move does not change directions, so it will maintain the heading of 90 degrees. As we turn back to the reload station, we need to position the grabber to be backward from the initial orientation. So we will set this as 180 degrees. The move forward to pick up the ball is at the same heading, 180 degrees. As we move to turn back to face the scoring tower, we need the robot to once again turn to 90 degrees prior to moving forward. Let's watch the validation run. For this run, I have changed the random jump simulator to be more aggressive, allowing a random direction plus or minus 10 degrees from the firing location. You can see in the sensor reading that the robot doesn't care what the random jump is. It compensates for the change prior to the next movement. We don't need to watch the entire validation, it is very consistent. That wraps up the basics of moving with headings, but before we start programming, let's talk about homing your robot. Homing makes sure the robot begins in the exact same position and orientation every time, which is crucial for accurate navigation. For your robot to navigate correctly, it needs to calibrate itself digitally after being placed in position. This process is called homing the gyroscope. The gyroscope helps the robot measure its rotation and direction, but it needs to know what 0 is. Before the event, your program should include a command to reset the gyroscope, setting 0 degrees as the starting direction. This ensures all future headings are based on a consistent reference point. By homing the gyroscope and starting from the same physical position, you reduce errors from the beginning. This helps your robot stay precise and reliable throughout the challenge, setting it up for success. I am showing you a screenshot from a robot set up for competition, so some of the commands may look different. You can see how we approach homing the robot. We have added an IQ Touch LED. This device, called andon in the code above, changes color and acts as a button. Generically, an andon light is a special signal light that shows if a machine or process is working correctly, needs help, or has a problem. You have probably seen these on self-checkout lanes. They are the lights that let you know if a lane is available for use, if it is in use, or if the person using it needs help. I use this IQ Touch LED as an andon. IQ Touch LEDs can also function as a button to trigger an activity. We use this to trigger the robot at the beginning of the autonomous competition. Let me walk you through this code. The when started control was moved to a new block. Our first line sets a variable called ready to 0. We will use this variable to ensure the robot has homed prior to starting the automation. You will see this in the column on the right momentarily. The next line sets the andon color to red so the operator knows that the robot is in the homing phase. If you move the robot after the homing begins, you must restart the homing process. The next action, in light blue, calibrates the internal brain. This is what tells the gyroscope to return back to 0. The fire variable pulls the firing mechanism into the down position so it is in the ready position. For other types of robots, this is where you would enter any commands that prepare the robot for competition. There is a 4-second delay so the robot can ensure it is finished, and then the ready variable is moved to 1. This enables the start command, which will be seen in the new action manager on the right. The andon is turned green. This tells the human operator the robot is ready to function. When the referee starts the timer for the autonomous skills test, the operator taps the IQ Touch LED and the robot is off. Let's look at the code on the right. This is what is added to the original when started series of code that controls the action of the robot. The when started command is replaced with a when pressed command, and we have added an if-then gate to ensure the robot has completed the homing process. In this situation, the entire original action manager code goes under else. For those working on developing their coding skills, you could use a broadcast command here instead of dropping the entire code in here. I encourage you to figure that out on your own. It is pretty easy. Because we use an if-else block, if the ready variable is not equal to 0, the action will not start until the homing process sets the ready variable to 1. If the user touches the sensor before homing is complete, the robot will play the siren sound. Once the ready variable is set to something other than 0, tapping the IQ Touch LED will trigger the action under else. This will put you off to a strong start. I hope to have time to make some other videos that discuss other opportunities to use sensors to aid in controlling your robot.